Okay, this is not a normal structure science episode. This is a technical deep dive into the problems of writing big functions in code. So if you don't like mathematics and equations and statistics, click away now. There are many reasons why big functions are bad and small functions are good. I'll use the word function here instead of method, even though I'm only talking about Java. Big functions are harder to understand, for example. They don't adhere to the single responsibility principle and are difficult to unit test. But these are largely subjective reasons. Are there any objective reasons why big functions are bad? Well, firstly, is there any such thing as an objectively bad function? Of course. In commercial software, a bad function is one that costs more. And each update or change to a function is a cost. A good function, commercially speaking, is one you write, commit, and never update. A bad function is one that you have to change and commit over and over again. So let's run with this. Let's say we have a program of 10,000 lines of code and it's structured into just two monster functions, one 8,000 lines long and one 2,000 lines long. We then supervise how this code evolves by analysing each new git commit made during development and noting which functions change. After a couple of years and hundreds of git commits, let's say all the code remains in those two functions of roughly 8,000 and 2,000 lines of code. In which function will most of the updates have taken place? It sort of feels natural to assume that around 80% of the changes would be in the bigger function and 20% would be in the smaller. Doesn't that feel unsurprising? What we're doing here is making what seems like a perfectly valid assumption. We're assuming that each line of code is equally likely to change. That the changes are uniformly, randomly scattered over the lines of code. Making this simple assumption, we can easily show why big functions are objectively bad. Let's say now that we have a real-world program rationally decomposed into 1,000 functions of varying real-world sizes. How do we compare its small and big functions? We do that by trying to say something about the average behaviour of functions. If you read that the GDP of Japan is $4 trillion and the GDP of Germany is $3 trillion, does that mean that the Japanese are more productive than the Germans? Well, no, because to see productivity you need to see the GDP per capita. Japan generates $37,000 GDP per capita. Germany generates $44,000. Just so, we're not so much interested in the total number of program changes over time. We're interested in the total number of changes per function. And we want to find out whether big functions change, on average, more than small functions. Let's conceptually divide our real-world program into 10 equally sized parts. That is, 10 parts, each with the same number of lines of code. They have to be equally sized like this because our assumption is that each line of code is equally likely to change. So having more code in one part would bias the results. Such a 1/10th part is known in statistics as a decile. Just as percentiles divide systems into 100 parts, deciles divide them into 10. Let's line up all the 1,000 functions of our program in order of increasing size. And, starting with the smallest function, let's put each consecutive function into the first decile until that decile holds 1/10 of all the lines of code in the system. We put the next functions into the second decile until it too holds 1/10 of all the lines of code and continue until all the deciles are full. Thus we'll have 10 deciles each with the same amount of code, differing only in the number of functions they contain. The first decile holds the smallest functions, the 10th decile holds the biggest. Thus, the first decile will hold a very large number of small functions and the 10th will hold a very small number of big functions. We're looking for the average cost per function within each decile. That is, what is the number of changes within a decile divided by the number of functions in that decile. Let's call this the decile average function change. But we're actually going to measure it in a second way too. We're going to measure the log of the number of changes divided by the log of the number of functions within each decile. This still captures the essence of what the average is, just flattens it slightly. But why would we do something like this? Well, as we'll see, we're going to be encountering a lot of wide-ranging data, even to the point of exponentials, which tend to obscure the underlying processes. Whereas taking the log preserves the essence of the data, but flattens it to an extent where we can make some simplifications, that is, some linear approximations, which greatly clarify matters. We'll call the two forms the linear decile average function change and the log decile average function change, and just bear with me. Okay, let's park the logarithms for a moment. Back in linear land, If we assume that each line of code is equally likely to change, then the number of changes in each decile will, over many commits, be roughly the same, let's say 300. So the decile average function change of each decile is 300 divided by the number of functions in that decile. But as we've seen, there are more functions in the first decile than the second. So the decile average function change of the first decile will be smaller than the second. And so on up to the 10th decile, which will have the largest decile average function change. To put this another way, the decile average function change is an increasing function of the decile itself. And as this is the most important line in this video, we'll give it a name. We'll call it the average cost relation. And it implies that big functions will on average cost more than small functions. Hopefully this is all rather obvious, but now let's measure it to see whether it's true. We randomly downloaded from GitHub a Java program called Atmosphere. We checked out a commit and analysed all its code, say 10,000 lines. We then checked out the following commit, analysed all its code again, and noted which functions changed. That's analysing another 10,000 lines of code, even though most will be unchanged. We did that for over 800 more consecutive commits, recording over 3,000 total changes over its, on average, 2,900 functions per commit. You very quickly end up analysing millions of lines of code. This graph shows the result, displaying the decile average function change, remember, the number of changes per function within each decile, against the decile itself. It goes up. The average cost relation holds for this program. But that's just one program. Regardless of how obvious all this sounds, we need more data. So we randomly downloaded more Java programs from GitHub and again analysed them to see how functions changed over time. Here's the full list. Couple of things to note, we didn't analyse entire programs as we lacked the CPU muscle, but made sure that the parts of programs analysed weren't trivially small. As you can see, there are at least 1,000 functions over at least 100 Git commits. Also, we analysed the bytecode rather than the source code, and bytecode can change just when a new JVM is introduced. So we split the entire history of the programs into parts. We'll call a part a Git commit series, where the JVM remained constant throughout. So one program can yield multiple commit series. Oh, and we'll get back to that last column later. Here's one of the new program's decile average function change plots. Yep, it goes up too. So does this, and well, that one doesn't. And that one certainly doesn't, but most do. Most show that the decile average function change increases with decile. The average cost relation mostly holds, over perhaps 80% of all the commit series analysed. And as that's over hundreds of millions of lines of code, it's not unreasonable to presume that it holds over 80% of all software. So we can say loosely, 80% of the time, big functions are objectively bad. We could end the video here. An assumption led trivially to a prediction that was verified by data. Except for two questions. Firstly, can we be a bit more precise about how the decile average function change increases with decile? And secondly, why does the average cost relation not hold over 20% of the code? It's all very well eyeballing messy graphs, but it would be great if we had an objective analytical measure of just how the average cost relation holds over the various commit series. And this is exactly what the log form of the decile average function change gives us, though we won't fully appreciate this until we examine its components. Because when we plot the log decile average function change, all those rather wide-ranging linear graphs collapse to, though nowhere near perfectly straight lines, graphs that look more linear than exponential. Here are some lovely straight graphs in our log realm of the commit series shown earlier. And here, and oh, not there, or there. As both the linear and log forms measure essentially the same thing, it's no surprise that both show the same few graphs do not conform to our expectations. And we can calculate just how straight these lines are. That is, we can calculate the degree to which the log decile average function change correlates with the decile. We get this by finding the standard Pearson correlation coefficient. Recall that a correlation coefficient is a number between -1 and 1. The closer to 1 the coefficient is, the more the data sets are linear. For this commit series, for example, we get a coefficient of 0.98. That's close to 1. And here are all the other correlations. The terminology is loose, but in general, anything above a correlation of 0.75 is called a strong correlation. So we can say that many of the log decile average function changes strongly correlate with decile. But really the benefit here is in sharply highlighting not the positive correlations, but the negative. We've put figures on those 6 brutes at the top. Those negative correlations imply that for those 6 commit series, 20% of all those investigated, smaller functions were on average more costly than bigger functions. Which leads to that second question. Why doesn't all code obey the average cost relation? What causes the 20% of outliers? Why is there a strong correlation for some programs but no correlation for others? The decile average function change is just the number of changes divided by the number of functions, all per decile. So let's take a look at both components, the function distribution and the change distribution, separately. Here are the function distributions for the 6 outlier commit series. It's well known that we programmers like to exponentially distribute our functions by size, so it's no surprise to see that all these commit series show falling exponentials. Here are a few function distributions of the programs that do obey the average cost relation, and they're exactly the same. They are all decaying exponentials. So whatever's causing the outliers, it's not the function distribution. Instead, we should have a look at the other component, how the changes are distributed over the deciles. That is, what is the total number of changes in each decile? Because our underlying assumption is that all lines of code are equally likely to change, then so each decile should have approximately the same number of changes. Here's the change distribution for outlier program JEDIS, which does not obey the average cost relation, and these changes are certainly not evenly spread over the deciles. This must be why our outliers don't obey the average cost relation, because their change distributions are not flat, but are more like falling exponentials. Okay, just to double check, let's confirm that the change distribution of the programs that do obey the average cost relation really are flat. Here's one of our star pupils. Oh, this program doesn't have a flat change distribution, even though it obeys the average cost relation. Its distribution is also heavily skewed towards the first decile. And the same is true for our next highest correlation, and for loads of the other commit series where the relation holds. So our grounding assumption that all lines of code are equally likely to change is completely wrong. Apparently code in the first decile is much more likely to change than code in the 10th decile. But we've already seen that the average cost relation holds for 80% of our commit series. It's a measured fact. So how do we explain it? Let's look again at our star commit series Bitcoin J, which showed that high correlation earlier. These are its function distribution and its change distribution. As they're both vaguely exponential, let's again change to a log scale. Now, neither of those lines is straight, but everything is linear if plotted log-log with a fat enough marker, so let's analyse the approximate case to see whether it gives us any insight. Let's take the least squares best fitting straight line approximation for both of these distributions. Why? Well, remember that the log decile average function change is just the log change distribution divided, value for value, by the log function distribution. But in our approximate analysis, both of these distributions are now straight lines. So what's the log decile average function change? It's just a straight line divided by a straight line, which gives us this wonderfully magenta line at the bottom. And recall that we're trying to explain that the decile average function change increases with decile for most programs. That is, we're trying to explain why the magenta line slopes upwards. We first note that the slopes of both approximate distributions are negative. They both go down. But the function distribution slope is steeper than the change distribution slope. That is, the function distribution has a more negative slope than the change distribution. So both distributions fall as we go up the deciles, but the function distribution falls faster. And as the function distribution is the denominator of the decile average function change, then this means that the decile average function change increases. That's what causes the average cost relation to hold. That's what makes big functions more costly on average. Or at least, that's an intuitive reading of the data, albeit with some heavy approximating. We can look at more programs where the average cost relation holds, and in each case we find that the slope of the approximate decile average function change is positive. In contrast, here are the graphs for the outlying programs that don't obey the average cost relation, and in all these cases, the approximate decile average function change goes down. Its slope is negative. But again, we don't really want to be eyeballing graphs and making intuitive readings. We want an analytical condition which is satisfied only when the average cost relation holds, at least approximately. And for that, we're going back to school. Every straight line is characterized by two parameters, its slope and its y-intercept. Remember this, baby? Y equals mx plus b. I knew you'd come in useful someday. M is the slope and b is the y-intercept. So we'll say that the approximate change distribution has parameters mc and bc. The approximate function distribution has parameters mf and bf. So what is the equation of the approximate decile average function change? Well, it's just mcx plus bc divided by mfx plus bf. What do you get when you divide a straight line by a straight line? Do you get a third straight line? Nope. When you plot this ratio for a program that obeys the average cost relation, you get this beast. Yes, the graph we've seen so far in the 1st to 10th decile range is just a segment of this thing. But note that the slope of this thing is positive everywhere. It slopes up to infinity, teleports back to the bottom of the universe, and just keeps on sloping up. Whereas here's a graph for a program that does not obey the average cost relation. It slopes down everywhere. So regardless of the oddness of this graph, the key to understanding whether a program obeys the average cost relation is to find the slope of this beast, and particularly to find the sign of the slope. If the slope is positive, the relation holds. If not, it don't. How do we find this slope? We differentiate it. Because you know, with all these lines and slopes flying around, that something was eventually going to get differentiated, and differentiated hard. Differentiating the beast gives this. Now, the denominator of this is, like me, square and always positive. So the sign of this slope is determined solely by the numerator, which is simply this. And this is precisely the condition we're looking for. This is what the final column was in our table earlier. At least to an approximation, when MCBF minus MFBC is positive, the commit series obeys the average cost relation. This is why those outliers don't obey the relation. The slope of their decile average function change is negative. But going deeper, to find out why this slope is negative for them, I really don't know. I'll have to actually study the program structure to see what's going on. But for now, there we have it. If someone asks you why big functions are bad, you tell them. In 80% of cases, the decile average function change is an increasing function of the decile. Yeah, that'll win the argument. One last thing. This may feel as though it's just some sort of statistics trick that plays no part in real-world software. No one, after all, orders a program into size deciles, so who cares? But it really does matter. You can easily see its effect. Let's take a look at the top 10 most expensive functions of one of our commit series. That is, which functions are updated the most, regardless of what size any of them are. If big functions are not more updated on average, then the top 10 most expensive functions will be randomly dispersed across all deciles. Or worse, it might even be biased towards the lower deciles, because those deciles have by far the most functions of the system. There certainly wouldn't be any special bias towards the higher deciles. Here's the list of the top 10 most changed functions for Atmosphere, ordered by the number of times each function was updated, but with the lines of code added for interest. Yep, that top function is changed 54 times over this particular commit series, but it's only 2 lines long. And 3 of the top 5 are certainly small functions. But look at the rest. 86 lines, 134 lines, 215 lines. These are big boys. Let's plot these 10 functions in their respective deciles. As we can see, 3 of the functions are in the 1st decile, but all the rest of the top 10 nasties are in the 8th decile or higher. And let's take the top 10 from all the commit series and plot them all together. There is our clear bias towards the higher deciles, exactly as the average cost relation predicts. If your company's bought out by a billionaire who decides to sack everyone who's worked on the top 10 most expensive functions of the year, you'd better hope you only worked on small functions. In 80% of cases, big functions really are more expensive, on average, than small functions.